Next, special types of relation. Special types of relation. There are mainly three types. One is reflexive, second one being symmetric, and the third one transitive. Reflexive relation, symmetric relation, transitive relation. Then if a relation is reflexive, symmetric and transitive, all three at a time, then we say the relation is equivalence relations. Equivalence relations. Right? Now let us discuss them one by one. Start with reflexive relation. First one. Reflexive relation. Reflexive relation. A relation R on a set A is said to be reflexive if every element of A is related to itself. Every element of A is related to itself. And here there is no only. I am not using the word only here. Means R is reflexive if AA belongs to R for all A belongs to A. This is a symbol for all. Ordered pair AA belongs to will be a member of this relation R for all A belongs to A. Then the relation R will become reflexive. Right? Clearly an identity relation is an example of reflexive relation. Means all identity relations are reflexive relations. Will the converse be true? Let us see. Let us see this. Let us answer this with the help of an example. If I take my set A equals to C, ABC, XY, let's say XYZ, X, Y, and Z, right? Here, every element of A is related to itself. So X is related to X, Y is related to Y, Z is related to Z, right? So this becomes a reflexive relation, and this is also an identity relation. But for reflexive, I can add one more element here, two more elements. X is related to Y also. This will not create any confusion here. I can very well add one or two elements apart from these three. The condition is for all A, for all small a belongs to A, ordered pair A must belongs to R. So all identity relations are reflexive, but all reflexive relations need not be an identity relation. Clear? Clear? Next one. Let us discuss now symmetric relation. Symmetric relation. A relation on a set A. A relation on a set A. On set A is said to be symmetric. Is said to be symmetric if and only if. This is if and only if AB belongs to R. This will also imply BA belongs to R. Meaning, if a relation R on A is symmetric, if AB belongs to R, this will imply BA also belonging to R. Means if A is related to B, then B must be related to A. If this happens, then the relation R becomes symmetric. Means for all A that is related to B, if this also implies B related to A, then the relation R becomes symmetric. Let us take an example. Let L be the set of, let us take L be the set of all lines in the plane. All lines in the plane. Plane means my coordinate plane. Now, L1 and L2, the ordered pair, small L1 and L2 belongs to R if, what is the relation? How is the relation defined? L1 is perpendicular to L2. L1 and L2, the ordered pair L1 and L2 belongs to R, means L1 is related to L2 if L1 is perpendicular to L2. L1 is related to L2 if L1 is perpendicular to L2. Now, if I can prove L2 is also related to L1, then the relation R on this set L will become symmetric. But we know if L1 is perpendicular to L2, then L2 is also perpendicular to L1. So clearly I can write from here L2 is also perpendicular to L1. If L1 is perpendicular to L2, if L1 is perpendicular to L2 is also perpendicular to L1, meaning L2, L1 is also belonging to R, means L2 is also related to L1. So I started L1, L2 belongs to R. I prove L2, L1 also belonging to R, means R, the relation R on the set of all lines, this relation R, which is defined as L1, L2 belonging to R, such that L1 is perpendicular to L2. This relation of perpendicularity defined on the set of all lines is a symmetric relation. Clear? You want to see one more example? Let's see one more example. Let A be a non-empty set and P of A, capital P of A. What is P of A? Capital P of A, we use capital P of A to denote the power set of A. Most of you will remember power set of A is the all possible subsets of A. All possible subset of set A is the power set of A. Right? Now, if I define for any two sets, say X and Y, belonging to P of A, X is related to Y if X is a subset of Y. Means the ordered pair XY belongs to R if the condition is X is a subset of Y. Then from here, can I write Y is a subset of X? If X is a subset of Y, Y may not be a subset of X. Means Y may not be related to X. Means YX may not belongs to R, will not always belongs to R. Means this relation of subset defined on the set A, on the power set of A, will not be a symmetric relation. Right? The third one, transitive relation. A relation on set A is said to be transitive if and only if AB belongs to R and BC also belonging to R, means A is related to B, B is related to C, and from this if I can write AC also belonging to R, then the relation becomes transitive. Means A is related, this is given, A is related to B and B is also related to C, this is given. From this to if I can infer, if I can write A is related to C, if I can write A is related to C, then the relation R on the set A becomes a transitive relation. Correct? Example, let us take an example. Let R be a relation. R be a relation is defined on the set of natural number. Right? How is it defined? XY belongs to R, means XY, the ordered pair belongs to R. What is the condition? If X divides Y. If X divides Y, then the ordered pair XY will be a element of the relation R defined on the set of natural number. Right? I have to prove that this relation is, let us see whether this relation is transitive or not. Right? What will do? I'll take the first two conditions. XY belongs to R, YZ belongs to R. Now if I can show XZ also belongs to R, if I can show that XY also belongs to, XZ also belongs to R, then the relation R becomes transitive. Let's see, let's try to prove this. XY belongs to R means X divides Y. Now if X divides Y, Y can be written as some K times X, because if 2 divides 10, then 10 equals to 2 into 5. So Y can be written as K 1 into X. Similarly, if Y divides Y and YZ belongs to R, means Y divides Z, means Z equals to K2 times Y. So here I can write your Z. What is Y? Y is K2 K1 X, means Z equals to K1 K2 times X. means z equals to some multiple of x, means x divides z, x divides z, means xz belongs to R. So the relations becomes transitive. Relations are defined in the set of natural lemma becomes transitive.